Hello all, welcome back to Chapter 7b, so still quantum theory and the electronic structure of the atom. So we saw this table in the last part in Chapter 7a, so on quantum numbers, n, l, m sub l, and m sub s. L we've been referring to as the angular momentum quantum number, and then these are a few different equations that could be helpful. So the maximum number of electrons in terms of n, the principal quantum number, is 2n squared. If n were equal to 1, for example, that would be 2 times 1 squared. So 1 times 1 is just 1. So that's 2 electrons that are possible within n equals 1. Then we define the subshell as the combination of n and l. And then the maximum electrons allowed in each subshell is 4l plus 2. Let's say, for this case, let's do n is equal to 2. So if n is equal to 2, the possible values for l is 0 up through n minus 1. In this case, for n equal 2, l can be 0, then 2 minus 1 is 1, so l could be 0 or 1 for a value of n equal to 2. So if L were equal to 1 in this case, we could say 4 times 1 plus 2, so 4 plus 2 is 6. For n equal 2, L equal 1, there are 6 possible electrons within that subshell. So let me also clarify a shell versus subshell versus orbital as far as the terminology. The shell is what we refer to as electrons with the same value of n. So they're in the same shell, means they have the same value for n. Next, if we're talking about the subshell, again, that's n and l. So electrons with the same values of both n and l would be considered in the same subshell. Now for the orbital, we get even more specific. So this is electrons with the same value of n, l, and m sub l. So electrons can have the same n, l, and m sub l, but they cannot all have the same n, l, m sub l, and m sub s. For m sub s, we have spin up or plus 1/2 and spin down as our other option. So minus 1/2, this describes one electron only, this describes one electron only. So electrons can have the same n, l, and m sub l, but no two electrons can have the same n, l, m sub l, and an m sub s. Because for m sub s, that describes just one electron here. So one electron here, a second electron here. But with n plus 1/2 for an ms value, again, that can only describe one electron, minus 1/2, only one electron. So two electrons cannot have the same n, l, m sub l, and m sub s. So this gets into this concept of the Pauli exclusion principle. So this says that no two electrons in an atom can have the same exact 4 quantum numbers. They can have the same n, l, and m sub l, but for two different electrons, that has to be two different m sub s values. One would be plus 1/2, the other would be minus 1/2. So again, from Pauli exclusion principle, no two electrons in an atom can have the same exact 4 quantum numbers. So an analogy here that can help us remember that is that each seat in an auditorium or a stadium can only have one person sit in it. They could be in section E, row R12, then seat 8. Only one person can be in that specific seat, just like only one electron can have the same 4 quantum numbers. Two electrons in an atom cannot have the same 4 quantum numbers. These 4 quantum numbers in an atom describe, again, just one specific electron. So one specific electron for each of the 4 quantum numbers. Then as a reminder from something we looked at previously in chapter 7, for L equal to 0, that's an s orbital, L equal to 1, a p orbital, L equal to 2, D, L equal to 3, F. So here's L equal to 0. These are all s orbitals. We also learned that s orbitals are all spherical. And then that number here describes the n. So n equal to 1, n equal to 2, n equal to 3. That s out here describes that L is equal to 0 for all of these. What is this combination of an n and an L value? Well, for every n and L, this is a subshell. So electrons that are in the same subshell have the same values of n and L. Then in this scenario, n is equal to 2, and we have p orbitals. So that's when L is equal to 1. Can we have n equal to 1 and also have a p orbital? Well, let's see, n equal to 1, L can be 0 up through n minus 1. So n equal to 1, 1 minus 1 is just 0. When n is equal to 1, the only possible L value is 0. That is a spherical S-shaped orbital. When n equals 1, L can't equal anything except 0. So now when talking about p orbitals, we had to jump up a value for n. So these are all n equal to 2. So when n is equal to 2, the possible L values are 0 up through n minus 1. So that is 0 and 1, right? 2 minus 1 is 1. So when n equals 2, the possible L values are 0 and 1. For p-shaped orbitals here, it's clear we have an L value of 1 for these examples. And so when n equals 2 and L equals 1, there are 3 different p orbitals that will exist for that atom. P orbitals always come in groups of 3. You will always see px, py, and pz. They may not be filled with electrons, each orbital, but p orbitals always come in 3. Px, py, and pz. And up to how many electrons can each orbital hold again? Well, up to 2 electrons in each orbital. So for an s orbital, that can only hold, each of these s orbitals can only hold up to 2 electrons each. Then for p orbitals, these come in groups of 3. This px orbital, py, and pz, out of all of these p orbitals, how many possible electrons can all of these hold? Well, there's 3 orbitals, so all of these combined can hold up to 6 electrons altogether. These are each individual s orbitals, so each one of these can hold up to 2 electrons. One way to remember this with the p orbitals is you could imagine we could possibly have an electron here, 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 and here. So up to 6 electrons within our p orbitals. I put an image of the different orbitals, so s, p, d, f, in 7a part 2. Here's looking at d orbitals. If you want to see f orbitals, you can go to that other chart in 7a part 2. So when L equals to 2, we have d orbitals because of this chart here, this table here. L equal to 2, we have d-shaped orbitals. Within d-shaped orbitals, these always come now in groups of 5. So like the p orbitals came in groups of 3, d orbitals come in groups of 5. Up to how many electrons can all of these d orbitals hold if there are 5? So in the d orbitals, these can hold up to 10 electrons apiece. So 2 electrons per orbital. In this case, you can't remember it as how many lobes is how many possible electrons, because just this one orbital can hold up to 2 electrons, but there are 4 lobes. This one, 2, up to 2 electrons, etc., for a total of up to 10 electrons for these 5 d-shaped orbitals. So for all of these examples, we have n equal to 3 and L is equal to 2. Can we have d-shaped orbitals when n is anything less than 3? Well, let's see. Let's say n is equal to 2. The possible values for L is 0 up through n minus 1, so that's 0 and 1. That means when n equals 2, can we have a d-shaped orbital? Well, 0 and 1 just describe s and p. So to get a d orbital, we have to be at an n value of at least 3 for L to possibly be equal to 2, which means we have a d-shaped orbital. For f orbitals, just to close the circuit here and all the types of orbitals we could see, these come in groups of 7. So in groups of 7, up to how many electrons can f orbitals hold? So 7 times 2, that's up to 14 electrons amongst the group of 7 f-shaped orbitals. And again, check back 7a part 2 for a diagram of all the different s, p, d, f-shaped orbitals. Let's try this example problem 7.8. So list the values of n, l, and m sub l for the 4 orbitals in the 4d subshell. Subshell describes the n and the l value. So here n is 4, right, because of that 4 here. Here d means we have what value for L again? So S, P, D, F, 0, 1, 2, 3. That means our L value is equal to 2 because we're told we have a d orbital. So here's our n, here's our L. What are possible m sub L values? To look at this, we just check out that L is equal to 2. M sub L can be minus L, including 0, up through positive L, and these all have to be integers. So these possible values here, minus 2, minus 1, including 0, then 1 up through plus L, so up through plus 2. So in the strategy for solving this, we just went through, we looked at the relationship between n, l, and m sub l. For 4d, that 4 out front represented our n. D means we have L equal to 2. All right, so L equal to 2 when we have a d orbital listed here. Then to find m sub L, we didn't need to look at n anymore. We just look at the value for L and go negative L, including 0, through positive L. So the solution to this problem is our m sub L can be minus 2, minus 1, 0, 1, or 2, all with the same n equals 4 and L equals 2 subshell values. Then all of these possible numbers represent different placements of the electrons. What does that mean? Well, L equal to 2, we're dealing with a d orbital. Let's go back and look at all the possible shapes of the d orbitals. Given that m sub L we just figured out can be 1, 2, 3, 4, 5 different possible values. How does this make sense based on what we know about d-shaped orbitals? Well, here there's 1, 2, 3, 4, 5. These all correlate to minus 2, minus 1, 0, 1, and 2 for the m sub L values we just figured out in that practice problem. So 5 different possible values here make sense for d-shaped orbitals where there are 5 different shaped d orbitals. D orbitals come in groups of 5. That 5 here should reflect all the possible m sub L values. What about for the other types of orbitals? So for L equal to 0, that's an S-shaped orbital. The possible m sub L values for an S-shaped orbital, L is equal to 0, m sub L is just 0. That makes sense because there's only one shape for an S-shaped orbital, it's one sphere. What about for P? L is equal to 1 here. The possible m sub L values then are minus 1, 0, and plus 1. This makes sense for p-shaped orbitals because there are 3 different shapes, px, py, pz for the p orbitals. For d and L is equal to 2, we just figured out that m sub L can be all of these 5 different possible options. And that makes sense because for the d orbitals, there are 5 different shaped d orbitals. So these 5 different shapes here. For s, there's only one shape orbital. It's just a sphere each time. These all have different values of n, right? So these are all different shells in general. So this is entirely different shell, entirely different shell, entirely different shell, because we define the shell as the n value here. Then for p orbitals, here's our px, py, pz. These are all from the same shell. More specifically, these are all from the same subshell. They all have the same n and l value. So this is what we expect for m sub l values according to how many different shapes there are for the orbitals. 1s, there are 3 p orbitals, 5 d orbitals, and 7 f orbitals. How does that make sense for f? Well, m sub l can be -3, -2, -1, 0, 1, 2, 3. That is indeed 7 different options, 7 different numbers, which makes sense for the 7 different f orbitals. Then we weren't asked about this, but what about the m sub s values? Remember, 2 electrons from the same atom cannot have all 4 same quantum numbers. Why does m sub s have to be different? Well, if we go back to the d-shaped orbitals, this can hold up to 2 electrons, this one, this one, this one, and this one. Within the 2 electrons this one can hold, one has to be spin up. The other electron in this specific orbital would have to be spin down. Remember, we define orbital as the n, l, and m sub l all together. So this is how m sub s fits into all of this. We weren't asked about this, but that's also why 2 electrons cannot have all the same 4 quantum numbers. 1 electron here would have to be spin up, or plus 1/2 for the ms value. Then the other electron here would have to be minus 1/2 for the second possible ms value. And so again here for the p orbitals, we can have 2px, 2py, and 2pz. This makes sense given how many different possible m sub l values there can be for a value for l equal to 1, which corresponds to p orbitals. So here n happens to be equal to 2 for all of these. Then for the p orbitals, that's an l value equivalent to 1. Right, get really used to writing out S, P, D, F, 0, 1, 2, 3. For a p orbital, L is equal to 1. So those are p orbitals. They have 3 different orientations in space. Again, a px, py, and pz. This makes sense based on the possible m sub l values. There's 1, 2, 3, matching up with 1, 2, 3. Then for d orbitals, we looked at this as well. So we know that our m sub l values could be -2, -1, 0, +1, or +2. So 5 different options, which makes sense for 5 different shapes for our d orbitals. So 5 different m sub l values, 5 different d orbital shapes. So shapes or orientations. Okay, let's do another practice problem to hopefully keep instilling this idea. So 7.9, what is the total number of orbitals? Let's define orbital. This is our n, l, and m sub l value. So how many different possible orbitals? We first need to be familiar with the definition of what is an orbital. So defined by n, l, and m sub l, associated with the principal quantum number of n equal to 3. So again, these definitions are going to come back again and again. So the shell, just the n, subshell, n and l, orbital, n, l, and m sub l. So to determine the total number of orbitals, remember that's n, l, and m sub l for a given n value, we first need to write the possible values for l. Then from L, we can determine how many possible m sub l values, and then that will be our final answer. For n equal to 3, L can be 0 up through n minus 1. That means this can be 0, 1, and through 2, right? N minus 1 is 3 minus 1. That's equal to 2. So for n equal 3, L can be an s, p, or d orbital. So L can be equal to 0, 1, or 2. For L equal to 0, the possible m sub L values, it's always minus L up through 0, then to plus L. For L equal to 0, we can't have negative 0, we can't have positive 0. That's just an m sub L value equal to 0 in this case. Let's do L equal to 1. When L is equal to 1, m sub L can be minus 1, 0, and plus 1. Right, because our L value is 1, so those are 3 different possibilities for m sub L when L is equal to 1. Then let's do L is equal to 2. M sub L can be minus 2, minus 1, 0, 1, and 2. So from this n value, we have 3 different possible L values. Then we wrote out our possible m sub L values given those values for L. So here's our answer, n equal to 3, L can be 0, 1, and 2. Then it's good practice to write this out too. When L is equal to 0, that means we have a 3s. This is a 3s subshell, right? Just n and L together. So that is a 3s subshell. When we include the m sub L value here, then we call that an orbital. So we can here, if we state n, L, and m sub L like we've done here. Then for n equal to 3 and L equal to 1, that means we have a 3p subshell. Then if we include the m sub L value, we can call that then a full orbital. So 3p subshell with the possible m sub L values of -1, 0, and 1, those are each of our 3 orbitals. So there are 3 3p orbitals described by the 3 m sub L values. For D, we're knowing that n is still equal to 3 here. D is equal to 2. D means that L is equal to 2. But when we're stating the subshell, we would just say a 3D subshell. Then if we include the m sub L values, the 5 possible m sub L values, which lines up with what we expect for d orbitals, then we call those all separate orbitals. So 5 different possible orbitals for n equal 3, L equal 2, for the 5 different possible m sub L values. We looked at these 2 equations in slide 2. We can also check our answer with one more kind of equation. The total number of orbitals for a given value of n is n squared. Total number of orbitals, again, we have to state the n, L, and m sub L to all describe an orbital. How many possible orbitals for n when n is equal to 3? So n equal to 3, 3 squared is 9. Does this line up with what we found? Well, let's count them. So here's 1 orbital, here's 2, 3, 4, 5, 6, 7, 8, 9. All these different m sub L values with their specified n and L values. We have 9 of these total, so 9 different orbitals for a value of n equal to 3. That does match up with this equation. Then there is example 7.10 in the main slide deck for a similar practice problem, so I recommend getting as much practice as you can with this concept in case it is really new. Once you get down the pattern and feel comfortable, especially with this table, then you should feel more comfortable with this style of problem. Let's go on to this topic now. So drawing a box diagram of the electron configuration in an atom. So we're going to talk about the different scenarios for either an atom with a single electron, we know that's just hydrogen, or if we have one of our other really low atomic number elements that lose multiple electrons to end up with one single electron, we could have this scenario as well. Generally, we're going to work with atoms that are multi-electron atoms. For multi-electron atoms, this statement holds that we talked a bit about in 7a part 2, where the energy depends on the value of N and the value of L. When there's only one electron to deal with, then the energy only depends on the value for N. So for instance, again, if there's only one single electron we have to work with, then we only need to deal with one electron here. We're not going to go on to fill any other subshells with electrons when there's only one electron we're working with. Let me talk a bit more about this energy scale here and what's going on. So we have energy here on the y-axis. This is the lowest energy. This is the highest energy here. Notice here we have our different subshells, so 4F, 4D, 4P, etc. So each of these is one subshell. So here's one example of a subshell. Then each of these lines denotes an individual orbital. Each orbital line can hold up to 2 electrons. Each orbital line here can hold up to 2 electrons. If there is only one single electron to deal with, then that can either be spin up or spin down. When we're filling electrons based on how many electrons are in an atom, we start with the lowest energy, then we work our way up. So if we're going to add in the 1 electron here to this diagram, then we can add in, let's say spin up is the only electron, and we made it spin up. If there were a second electron to deal with, we would fill this line with a spin down. Here though, we're just looking at an example with a single electron, so we could fill that 1s subshell with 1 electron being either ms equal to plus 1/2 or ms equaling to minus 1/2. So if this 1s is the subshell, what is the exact orbital? Remember, for the orbital, we need the n value, the l value, and the m sub l value. When s is equal to 0, that's an l value equal to 0. The only possible m sub l value is 0. For this red line here, that's one orbital. That is n equal to 1, l equal to 0 because of that s here, and m sub l then equal to 0. So this is our orbital. We filled it with 1 electron being either spin up or spin down. Let's talk about a more realistic scenario that we'll more often look at for a multi-electron atom. We have the same exact concept here, that we still fill our electrons from the lowest energy to the highest energy. Each of these red lines still denotes an orbital with a specific n, l, and m sub l values. Within each orbital can hold up to 2 electrons. So within each red line here, we can fill that with up to a spin up and a spin down, where this represents 1 electron as spin up, this represents 1 electron as spin down. The order of energy here is a little bit unique, where 1s is the lowest energy subshell, then 2s, then 2p, then 3s, then 3p, then 4s, then this is kind of the more rare or exception we could see. So after 4s, be careful because next comes 3d. Again, we always fill electrons from the lowest energy possible to the highest energy possible. Lowest energy is more stable. Lower energy, more stable. If we're at some higher energy, that's going to be not as stable. For an electron to be at a higher energy subshell, that means it can more easily get plucked away from the atom. The electrons that fall down here in the inner subshells, those are more stable. It is going to be really important to understand this order here of the subshells. So 1s, 2s, 2p, etc. going up. Let's talk more about how we start to fill in all these electrons. So for example, we could have something like carbon that has an atomic number of 6. That means carbon has 6 protons and 6 electrons. We can use this diagram to show the energy levels and the subshells that will find those 6 electrons in. So what that's going to look like is drawing in 1 electron, the second electron, so 1, 2, 3, 4, 5, 6. Notice that I drew in these electrons like this for the 2 because we fill this subshell, then we fill this subshell, then for this set of orbitals, we fill in 1 electron in one direction at a time. Let's talk more about this. This is in terms of the Aufbau principle. For the Aufbau principle, a really important principle here is that we fill up electrons in the lowest energy levels, the lowest energy orbitals first. That means we fill in 1s, 2s, then 2p. So notice for carbon, I filled the 1s, I filled the 2s, then I partially filled the 2p. We'll talk about why I did that in a second too. For the Aufbau principle, we're filling up the lowest energy orbitals first. So we filled up 1, 2, 3, 4, 5, 6. I want to talk more about why I did this within the 2p orbitals. The 3 2p orbitals, I should say, to be clear. So for the 1, 2, 3, 2p orbitals, just to not be confusing. So the reason I did this is because we also need to follow Hund's rule. The most stable arrangement of electrons within subshells is the one with the greatest number of parallel spins. In other words, we want to only pair up electrons if we have to. Otherwise, we'll do as many unpaired spins as we can. So we'll fill up 1, 2, 3, 4. Then for these 3 2p orbitals, we're not going to do this. We won't do 1, 2, 3. We want to keep as many unpaired as we can. So for these 3 orbitals, we'll do 1, 2, 3. This is correct. An empty one here, but with paired here, is not correct, according to Hund's rule, which we follow when filling up these electron diagrams. I mentioned this order would be really crucial to know, so you could memorize this, write this on your note card, the lower energy up through the higher energy, with this careful exception here. 1s, 2s, 2p, 3s, 3p, 4s. This is our kind of different sort of exception here, so just watch out for this one. You may have learned to memorize this order if you drew something like this in a previous chemistry class. If you haven't, don't worry. Just write down this order somewhere, or even draw this diagram on your note card. The way this diagram helps is we have 1s first, then 2s, then 2p, 3s, then 3p, 4s. Then it makes sense why we go to 3d next, then 4p, 5s, etc. The reason this looks like an exception is because we're going in increasing n, so n equal 1, n equal 2, 3, 4, then n equal 3 comes in here. What is the L equal to here if this is a d orbital? N equals 3, L equals 2 for a d orbital. And we always fill in electrons from the lowest energy through the highest energy, so this order here is really important. Here's an explanation here as well to give you a little more context. I touched on each of these points, but this isn't written out for you if it's helpful to read through. For instance, here we're writing out n equal 1, n equal 2, n equal 3, all these different rows. Then each column should be all of our S, P, D, and F. Then we draw a line from the upper right-hand corner to the lower left corner for the first row, so just one S. Then go back to the next row's upper right-hand corner and draw diagonally again. Repeat this process until you have all this different order for the different subshells. So filling in order from increasing energy, so lowest. You want to start here at the lowest energy, then fill up through increasing energy, so then we go up to the highest energy. Start with the lowest, then work your way up to the highest energy subshell. What we've been talking about so far is the electron configuration. So to define this, an electron configuration is how the electrons are distributed among the various atomic orbitals within an atom. So far, we've seen a lot of N and L to make up our subshell. Right, so we saw 3s, what else? 2p, 3d, 1s, etc. So we saw all these subshells from the N and the L value. So that's this portion here. Then this is raised to an exponent, and that exponent reflects the number of electrons in the orbital or the subshell. Subshell is the N and L together. The orbital is the N, L, and M sub L. For example, for our simplest element, as far as its atomic structure at least, so just one electron for hydrogen. It has one proton and one electron. How do we orient that one electron? It's going to go into the lowest energy subshell. The lowest energy subshell is 1s. To fill the 1s subshell, we only have one electron to put in, so we make it a spin-up electron. Then this reflects a 1 for the exponent here. How we say this now is the electron configuration of hydrogen is 1s1. The principal quantum number N, S, our angular momentum quantum number L, and then the exponent is how many electrons there are within that subshell or orbital. We can do this for every single element: hydrogen, oxygen, lithium, etc., barium. Based on how many electrons there are, we can fill in these energy diagrams, again, from the lowest energy up to the highest energy, until we run out of electrons to put into an energy diagram like this. Now, like we saw from Hund's rule, we're only going to pair up electrons if we need to within each orbital. If we don't have enough electrons to pair up like this, we're going to spread out the electrons so that they are unpaired. We'll only pair them up if we have to. Let's talk about these definitions then you should be familiar with. We can have paramagnetic. This is an unpaired set of electrons. If an element is paramagnetic, it has electrons that are unpaired. So paramagnetic, kind of the opposite that you might think. Paramagnetic, we have unpaired electrons. Diamagnetic, if an element is diamagnetic, that means all electrons are paired within that element. If we completely fill up the 2p subshell, for example, then that is diamagnetic. We have 6 electrons, they're all paired. If, however, we only had 2 electrons in the 2p subshell, then those 2 electrons are going to be unpaired, leaving this to be paramagnetic. So para, unpaired, dia, all paired. Let's try this example. So example 7.11, what is the maximum number of electrons that can be present in the principal level for which n is equal to 3? Well, to find the number of orbitals, we tried that. That is n squared. So 3 squared is 9. That is 9 possible orbitals. Then each orbital can hold up to 2 electrons. So in the 9 orbitals, this is up to possibly 8 electrons. This is a standard fact here that each orbital can hold up to 2 electrons. We saw that previously. Just keep this guideline in mind. There is another way we could solve this as well, so I'll go through that. We're given a principal quantum number, so n, we can determine all the possible values for L, the angular momentum quantum number. Then I know there's a few different equations we've seen before, but the preceding rule shows the number of orbitals for each value of L is 2L plus 1. So if we're just focusing on 1L, we can calculate the number of orbitals as 2L plus 1. This equation we looked at here is just looking at the value for n. If we're just looking at n, it's n squared to tell us the number of orbitals. Here though, just looking at the value for L, that's 2L plus 1 tells us the number of orbitals. So for n equal to 3, L can be 0 up through n minus 1. That means this can be 0, 1, or 2. 3 minus 1 is 2. These are our possible values for L. Then let's use this equation now, given our values for L that we just determined. For each value of L, the number of possible orbitals is 2L plus 1. 2 times 0 plus 1 is 1. 2 times 1 is 2, plus 1 is 3. 2 times 2 is 4, plus 1 is 5. So either going from n, taking n squared to find the number of possible orbitals, or from L and taking 2L plus 1 to find the number of possible orbitals. We could also further prove this. We could just write out all the possible m sub L values like we've done before. When L is equal to 0, m sub L can only equal to 0. When L is equal to 1, m sub L could be minus 1, 0, and 1. When L is equal to 2, oops, this should be 1. When L is equal to 2, m sub L can be minus 2, minus 1, 0, 1, and 2. So we could use the n squared, or use the 2L plus 1, or just write out all the possible m sub L values. So if we wrote all the m sub L values out, that also tells us the number of possible orbitals. Let's see then, we have 1, 2, 3, 4, 5, 6, 7, 8, still 9 possible orbitals. Using this then, we still come back to this big idea that each orbital can hold up to 2 electrons. Remember back to this diagram that each of these red lines represented 1 orbital. So each of these red lines represented 1 orbital. Each orbital can hold up to 2 electrons, spin up and spin down. So we could solve this a few different ways like we did. We could look at n squared to tell us the number of orbitals, 2L plus 1 to tell us the number of orbitals, or find all the m sub L values to tell us the total number of orbitals. Then, of course, this comes back again here. Each orbital can hold up to 2 electrons. That makes our final answer for this problem 18. Let me tell you yet another different equation. This is similar to what we saw, but we could also find the total number of electrons by taking 2 times n squared. So just n squared tells us the number of possible orbitals, right? Then 2n squared tells us the number of possible electrons. So n squared, the number of possible orbitals, the number of possible electrons, 2n squared. So that's this equation here. Either way, when n is equal to 3, so 3 squared is 9 times 2, that's 18 possible electrons when the principal quantum number is n equal to 3. Let's try this practice problem where we draw out the electron configuration for the neutral atom of phosphorus. We are specifying this is a neutral atom because if this were a cation or an anion, the cation is positively charged, it's lost one of its electrons. An anion has gained an electron to be negatively charged, gained 1 or more electrons. Cations have lost 1 or more electrons. For this practice problem, we're going to draw out the electron configuration for a neutral atom of phosphorus but we will practice with ions. Here, this is not an ion, it's just the neutral form of phosphorus. So we know the electron configuration of an atom is the arrangement of electrons in it. Specifically, an electron configuration is the set of quantum states or quantum numbers to which an electron has been assigned. That electron will have an N, L, M sub L, and M sub S value associated with it. So this is for each electron, an N, L, M sub L, and M sub S value. One way to describe an electron configuration is with the diagram that we saw, so a box diagram. We're going to draw a box diagram for this practice problem. Let's look at this example of fluorine. Why is this the box diagram for fluorine? How many electrons does fluorine have? Let's look at the periodic table. Here's fluorine. Fluorine has an atomic number of 9. That means it has 9 protons and therefore 9 electrons. For the increasing order of energy, we have 1s, 2s, then 2p. We need to fill 9 electrons total. So for 9 electrons, we're going to fill this one first, then we have to pair it. We still fill it from least energy to greatest energy. And we do pair this pair of electrons if we need to move up in energy level and we haven't used all the electrons yet for that atom. So here's 2 so far, then 3, 4. We pair this right away before moving up in energy level. Now we have 5 remaining. To do this, we're going to fill in 1, 2, 3. First, all of these are unpaired. Do not pair within a subshell until you have to. 1, 2, 3. Now we have to pair. This is going to be 4, 5. It's somewhat arbitrary for which one we pair. We do usually denote it from left to right. So I paired this one, then this one. This one is currently unpaired. And we've used up the 9 electrons of fluorine. So again, we can take any element and draw a box diagram just like this one. And we'll practice doing that for phosphorus. Here's some other key facts we've gone through for box diagrams just to talk through them for more detail. First, each orbital is represented by a box. Orbitals in the same subshell are grouped together and given one label. For example, in that diagram, the 3 orbitals in the 2p subshell are all grouped together. So these are all from the same subshell. Here's one orbital, here's another orbital, here's another orbital. Those are all in the same line if they're from the same subshell. And the subshell again is denoted as the N and the L together. Those make up a subshell. Next, each electron is represented by a half-headed arrow. So for each electron, we can draw it like this or like this is also customary. Not like this, not a double-headed arrow, just a single-headed arrow. Spin down would look like this or like that. Next, each electron arrow can point up or down depending on the spin angular momentum quantum number, or M sub S as we know it. Usually we imagine the spin up to be ms is plus 1/2, spin down to be ms is minus 1/2. So minus 1/2 plus 1/2. Then again, this Pauli exclusion principle tells us that no 2 electrons can have the same exact 4 quantum numbers. That means each orbital can hold 2 electrons, but one of the electrons has to have an ms value of plus 1/2 or spin up. The other ms value for the other electron has to then be spin down, or an ms value equal to minus 1/2. Then the boxes are sometimes arranged so that their height tells us the relative energy of the subshells. For example, in the diagram, we can see the 2p boxes are drawn higher than the 2s box because the energy of an electron in the 2p subshell is higher than the energy of an electron in the 2s subshell. So 2p higher energy than 2s and 1s. So now we see these sort of relative energies spaced out like this from the heights of the boxes. So this one's shorter, next, and then next. That's fairly customary, so we can more easily visualize those different energy levels for the different subshells. Then continuing on, reminder of the Aufbau Principle again. The Aufbau Principle says the electron configuration of an atom has to be built up by adding electrons to orbitals in order of increasing orbital energy. Aufbau is German for building up. So building up lowest energy through highest energy. Lowest energy through highest energy is for the Aufbau Principle, and from the Aufbau Principle, we can follow the Aufbau method. To use this Aufbau method, we're going to practice. We could count the total number of electrons in the atom like we did for fluorine, like we will do for phosphorus. Then imagine the possible subshells in order of increasing energy. We may find it helpful to draw a chart in which the possible subshells are listed with N increasing up the rows, L increasing to the right along the columns. Then N plus L rule tells us that these subshells increase in energy as you go along the upward diagonals of this chart. We saw that chart. Let's look at this again so we could draw it like this as well. This is the flipped version of what we saw earlier. It's up to your preference entirely. Here, N starts at 1, 2, 3, 4, 5. Then L is 0, 1, 2, 3, 4. Now, instead, you could feel comfortable drawing it in this direction, N equals 1, N equals 2, etc. In the previous example, N equals 1 started down here. Either way is completely fine as long as you're comfortable describing from lowest energy to relatively higher energy. So you could write out the diagram this way to remember it. You could remember this order. Or if this way feels more comfortable to you, you could orient it such like this, where N equal 1 is lower, N equal 5 is higher. Whatever you'd like to do to get comfortable knowing that lowest energy, next, 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 etc., and electrons fill up in that manner. For instance, we fill the 1s orbital first, next 2s, then 2p, then 3s, 3p, 4s, then 3d, right? Don't forget that one exception, where n is equal to 3, but it pops in here, right? So 3d comes after 4s. So definitely find a way to feel comfortable knowing the order of these subshells to fill up electrons from lowest energy to highest energy according to the Aufbau principle. So in solving this practice problem, we can begin by drawing boxes and filling them up with electron arrows. We begin by drawing a box for the lowest energy orbital, or 1s, put one electron arrow in it. If we're drawing the diagram for hydrogen, where it only has one electron. If we have more than one electron, we keep putting in electrons. So for 1s, we would pair that right away. One spin up, one spin down, then we continue on in increasing order of energy according to this order. That's just for 2 electrons. We're going to continue adding boxes and doing this up for however many electrons we have, where each arrow represents 1 electron. For each of the p orbitals, we're going to have 3 boxes for px, py, pz. For the d orbitals, we're going to have 5 boxes for the 5 different shapes or orientations of those d orbitals. Remember, there are 5 here, 1, 2, 3, 4, 5 different orientations for our d orbitals. So for our d orbitals, 5 different ones, 5 different boxes then, where each box can hold up to 2 electrons because each box or each line represents 1 orbital. We should be clear about the energy levels and draw in those relative heights like we saw for fluorine. So like we saw for fluorine here, we should draw in these relative heights. And importantly, we're going to make sure we put no more than 2 electrons in each box or on each line, and make sure the arrows are paired, 1 spin up, 1 spin down. We'll pair electrons only if we need to. If we're filling up orbitals and we only have 1 more electron to fill in, it is customary to draw that one in as spin up rather than spin down, but either way is totally fine. So for instance, you would maybe think to draw it in like this. That's okay. That's okay and correct. This is more customary than drawing it in like this. So for 1 electron that's unpaired, drawing it generally as spin up. Then, of course, we're going to remember Hund's rule. For Hund's rule is when the orbitals in a subshell are not filled completely with the electrons. The electrons then are spread out as evenly as possible amongst the orbitals in that specific subshell level. So this is wrong, right? We have 3 different orbitals for 2p. So we do 1, 2, not pairing them. So we're not going to pair them. This is what it's going to look like. We're going to write out 1, 2. If there were a third one, we would draw that in as well. We don't want to pair electrons in an orbital until we need to. But within each energy level, we do pair those before moving up to the next energy level. So we would fill this, then move up, fill this. We would fill this if we had 6 electrons to fill in. We only have 2 here in this example, so just drawing in 1, 2, unpaired. Let's try phosphorus. So that has an atomic number of 15. That must mean it has 15 protons, then also 15 electrons. With 15 electrons, how many different orbitals are we going to need? 15 divided by 2, so 7.5. We're going to need 8 different orbitals to fill in. Let's look at what we need. So 15 electrons with 7.5 or up to 8 orbitals. So for 7.5 orbitals or 8 orbitals, let's see what we need. We're going to need, this is 1, this is 1, this is 3, right? Each p has 3 orbitals. So for orbitals, we have 1, 1, then 3. That's 5 so far. Then we'll need this one. That's another 1 single orbital. So that's 6 orbitals so far. Then if we include 3p here, that is also 3 orbitals. 1, 2, 5, 6, then 9. If we stop at 3p, we'll have enough boxes or lines or orbitals to fill in our electrons for phosphorus. So let's draw these in. We have 1s, 2s, 2p, 3s, and 3p. That's the total number of orbitals we need to draw in our 15 different electrons. Let's see how those fill up. Well, here we'd start and do 1, 2. Next, we fill this up completely before moving up an energy level. So 1, 2, 3, 4. Then to draw this one in for 2p, before pairing them, we'll draw in the individual electrons. We've used up 2 and 2. Then we draw in 1, 2, 3. At this point, we have not used all the electrons of phosphorus, so then we keep going and we pair these. 4, 5, 6. So 2, 2, and 6. That's 10 electrons so far up through the 2p subshell. Then for the 3s, we completely fill this one up, and then that's 12 electrons at this point. We have 3 more. For the 3p subshell that has 3 orbitals, we can think of that as px, py, and pz. We need to fill in 3 more electrons. We want them to be unpaired unless they need to be paired. In this case, we'll fill in 1, 2, 3. We don't need to pair any of these because now we've reached 15 electrons, the total number of electrons for phosphorus. This is our final correct answer to fill in this box diagram for the 15 electrons for phosphorus. If phosphorus became phosphide and was P3-, that means we have 3 additional electrons to fill in. For an anion for phosphorus with 3 additional electrons, can you think where those might go? So for the anion form, we are going to then pair up 1, 2, 3. That's only if we have the anion form of phosphorus with 18 total electrons. For this practice problem here, we are just asked to consider neutral phosphorus that has 15 electrons. So this is our final answer. We will do some examples with ions too. I'm going to include this animation here on electron configurations. Definitely let me know if you have any questions at all. I'll talk to you more for 7b very shortly. So I hope you're all doing well, and I will talk to you soon. I'm also including here some animations that are copyrighted, and they are provided by the publisher.
An electron configuration of an atom shows how the electrons are distributed among the various atomic orbitals. The periodic table is arranged to show which subshells are filled as we progress across and down the periodic table. Oxygen has an atomic number of 8, meaning that the atom has 8 protons and 8 electrons. To write the ground state electron configuration, we start with the 1s orbital and continue to place electrons in orbitals of increasing energy until we reach 8 electrons. Recall that any one orbital can hold at most 2 electrons. Starting with the 1s orbital, which can hold 2 electrons, we write 1s2. Next, the 2s orbital can hold 2 electrons. We write 2s2. We have placed 4 electrons, meaning there are still 4 electrons to place. There are 3 2p orbitals, which can hold a total of 6 electrons. We place the remaining 4 electrons in the 2p orbitals and write 2p4. The ground state electron configuration for an oxygen atom is 1s2, 2s2, 2p4. Double check that you have placed 8 electrons. 2 plus 2 plus 4 equals 8. We use a box to represent each orbital. We place electrons based on the Pauli exclusion principle and Hund's rule. 2 electrons are placed in the 1s orbital with opposite spin. 2 electrons are placed in the 2s orbital with opposite spin. We place 1 electron in each of the 2p orbitals with the same spin. The 4th 2p electron is paired up in one of the 2p orbitals with opposite spin. This is the ground state orbital diagram for an oxygen atom. Calcium has an atomic number of 20, meaning that the atom has 20 protons and 20 electrons. To write the ground state electron configuration, we start with the 1s orbital, which can hold 2 electrons. We write 1s2. Next, the 2s orbital can hold 2 electrons. We write 2s2. The 3 2p orbitals can hold 6 electrons. We write 2p6. Thus far, we have placed 10 electrons. The 3s orbital can hold 2 electrons. We write 3s2. The 3 3p orbitals can hold 6 electrons. We write 3p6. The final 2 electrons are placed in the 4s orbital. We write 4s2. The ground state electron configuration of a calcium atom is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Double check that you have placed 20 electrons. We can simplify this electron configuration by using the noble gas core configuration of the noble gas element that most nearly precedes the element being considered. In this case, the noble gas would be argon. The argon core configuration accounts for 18 electrons. We add 4s2 to account for the final 2 electrons. We start with the shorthand representation for the electron configuration of calcium. We add a box to represent the 4s orbital. The last 2 electrons are placed in the 4s orbital with opposite spin. This is the ground state orbital diagram for a calcium atom. Remember that the notation argon in square brackets represents 18 electrons. Nickel has an atomic number of 28, meaning that the atom has 28 protons and 28 electrons. Let's start with the ground state electron configuration with the noble gas core preceding nickel. We start with the argon core, which accounts for 18 electrons. We have 10 electrons left to place. We move to the 4s orbital, which can hold 2 electrons. We write 4s2. There are 5 3d orbitals, which can hold 10 electrons. We have 8 electrons to place, so we write 3d8. The ground state electron configuration of a nickel atom is argon, 4s2, 3d8. Double check that you have placed 28 electrons. Remember, the argon core represents 18 electrons. We use a box to represent each orbital. We place 2 electrons in the 4s orbital with opposite spin. We place 1 electron in each of the 3d orbitals with the same spin. This accounts for 5 of the d electrons. The remaining 3 electrons are paired up in 3 of the d orbitals with opposite spin. This is the ground state orbital diagram of nickel.